Hello students, so in this lecture we will be discussing about some important nanomaterials, but before going to that let us discuss what has been discussed in our previous class. Now what we have understood is that for the characterization of nanomaterials or any material for that instance, we require the very basic instrument, that is the XRD, and it is based upon two fundamental equations. One is called the Bragg's law, and the other one is it's called the Bragg's law. One second. Other one is the Debye-Scherer's equation. This one. Now, the Debye-Scherrer equation, it is based gives you the particle size d, and in the case of nanomaterial, since it is inversely proportional to the bandwidth or full width of maxima, a nanomaterial is supposed to give a broader width of its XRD spectra, simply to make the beta value more. So higher beta means, if beta increases, it means the particle size is going down. So for the case of nanomaterial, we require a much higher beta to give it a nanometric range size. So first identification is this. The next aspect that we studied is your nano indentation. Right. Nano indentation. Now, nano indentation process is mainly done for a very low precision indentation technique for nanomaterials and thin films, and it is based upon continuous stiffness mode measurement. Continuous stiffness mode measurement to get the hardness and the load depth plot for every initiated uh, interval of depth. So this is a typical plot that we obtain in the case of a nano indentation, and from these data we can find the hardness modulus and other properties as well. Okay. Now the another thing that was discussed was TEM, transmission electron microscope, and associated diffraction pattern analysis, that is the SAED pattern analysis. Now the reason why this electron is used for to see the microstructure of very low material or nanomaterial, that is simply because of the fact that the electron has a low wavelength. When electron since electron has got both wave and particle nature, if you look into the wave nature of electron, the electron wavelength is extremely low, of the order of Armstrong, so that matches with the nanometric size identification that you would like to have. That is why the electron microscope is used. So apart from the imaging a very small or microstructure of very low dimension, another aspect of TEM is the SAD pattern, which the full form of which is selected area electron diffraction. It means that we take a certain portion of the sample and we allow the electron to diffract through the sample. This creates a diffracted pattern, we have discussed previously. So in the case of zinc crystal, we have a spot pattern like this. However, in the case of a polycrystal, we have a ring pattern. In the case of an amorphous material, we have an halo pattern. And since the nanocrystalline material falls somewhere between amorphous and polycrystalline material, and it is sometimes called the near amorphous material, we The SAD pattern obtained in the case of nanocrystalline material will be basically the base will be hollow, but with still a little bit of rings of polycrystallinity will be there. And these analysis is done by this simple formula RD is equal to L lambda. Now this is an image of a TEM of a nanocomposite. You can see how small the material is. So this is, if this is 100 nanometers, you can roughly find out the radius of the or the size of the nanomaterial. This is basically a composite material which is a tribological coating. It's called tribocoat, and the corresponding SED pattern, you can, if you look, you would find this is actually an inverted picture. I mean, the original picture TEM is a bright light. The ones which are shown by dark lines are actually bright lines, so it has been inverted. Now here you can see different ring formation have taken place. So these all rings correspond to one phase of the material. So using this formula, we can calculate the D spacing, and from the D spacing we can have a little bit knowledge of what type of material is present here. R is the distance from the center to each ring. L is the camera length, and lambda is the wavelength of the electron. So wavelength electron means lambda is equal to h by root 2m ev. So whatever the value of v will be, on that the wavelength will depend. The higher is the value, the role will be the wavelength of the electron. Now, this is another picture that is shown here is that of an XRD. So this is an XRD of material tin oxide. You can see very sharp lines being present in the XRD, so it indicates that it is highly crystalline. And also all the there are different phases. I mean, there is also phases of SnO2 and ZnO. So a polycrystalline material can be seen through the XRD pattern. Had it been a nanomaterial, the peak intensity would not have been so high. The material would have been like this. So, so we can, due to this high value of B, the particle size actually decreases D, so it will have a broad spectrum. So in this lecture, let us talk about important material called the zinc oxide material. The reason it is being discussed is that probably it is the material having the highest number of nanostructure options. That it can be a sheet, it can be a wire, it can be a belt, it can be a dot. Now, zinc oxide has very good optical properties. It is used in the case of transport electrodes, and chemical synthesis of zinc oxide is a little bit difficult because of its high vapor pressure. So preferably for device fabrication and for sensing fabrication, zinc oxide is deposited in the form of a film or a thin film, which is a two-dimensional nanostructure. So here thin film is a two-dimensional nanostructure, as one-dimensional nanostructure would have been a wire and zero-dimensional would have been a dot. Now this thin film of zinc oxide, when deposited, they have got a preferential direction, that is 001 direction, and they can be deposited by various means, like you can have molecular beam epitaxy, pulse laser deposition, magnetron sputtering, metal organic chemical deposition. So let us discuss each of these methods one by one. The molecular beam epitaxy, the basic, the major requirement of a molecular beam epitaxy is it should be ultra high vacuum. That is about 10 to the power minus 11 torr. This should be the vacuum level inside the chamber, because we would like to have the film. Since it's an epitaxial, mainly made for the epitaxial growths, and 100% purity, or not 100%, I mean close to 100% purity is desirable. And then the Newton number, it has the source of which the film has to be deposited. It is put inside this Newton cells, and they are they are subjected to heat, and evaporation occurs, and the material go and sit or get deposited as a film. Now, for an vacuum level, this number, this lambda by L number, should be always equal to 0, where lambda is the mean free path of the electron and L is the path length or camera length or whatever. Uh, I mean the path length, the chamber length, not the path, no, not the camera length. So the basic idea is that lambda, mean free path, means the distance traveled by electron between two collisions. So if we make the vacuum in such a level that this lambda is much larger, that when it undergoes very less collision, or the gas molecules inside the chamber, which is basically initially oxygen, they undergo very less collision, so the vacuum level will increase. Okay, and so this is how the film deposition takes place. You can have a pulse laser deposition technique as well to deposit zinc oxide. Now, in the pulse laser deposition is based upon ablation, is breaking down. So, and it is also so a laser, NDYG laser is used, and they are used in the ablation of zinc oxide, and with in the presence of a high purity oxygen. So the process is that when it undergoes the ablation method, the ablation after the ablation method has taken place, the oxygen present in the chamber, they make this ablated material go and stick onto the substrate, forming a high purity film. Next process of film deposition is the banditron sputtering. Now, the banditron means basically a device where you have circular magnets put in this circular fashion, so that one gets an E cross B field at the center. The idea is to confine the electrons which are formed due to plasma when the plasma struck, confine them locally and in the line of sight. This is the areas, and this is achieved through this banditron sputtering technique. Now, for banditron sputtering, we require high vacuum, not ultra high vacuum. And for getting high vacuum, uh, rotary pump as well as diffusion pump containing silicone oil is sufficient. So, this is how the plasma structs after the argon gas is introduced into the chamber, and we can do based upon the substrate, we can have the deposition. Now, this Vanatron sputtering comes in two different modes. One is RF and DC. And since the target is kept here, see, this is the place where the target is kept, and it is kept at a negative potential. So, a self-induced negative bias occurs in the case of an RC, because if we are using RF, we mean that we are alternately changing meaning the polarity of the target and the anode, of the cathode and anode. Now, even if the polarity changes, since the mass of the ions is much larger than mass of the electron, so the electron, although the electron they change their poles very fast. However, it takes a lot of time for the mass to do so. So that is why the electron creates a self-induced negative bias behind the neutron, and so induced bias causes higher uh, attraction of positive ions of the gases, causing sputtering. The next method is called metal organic CVD, where metal organic precursors like metal halides and metal alkyl are used to deposit zinc oxide. Metal alkyls will mainly uh, zinc chloride and zinc iodide, and metal alkyls consist of CH32Zn and C2H65Zn, dimethyl zinc and diethyl zinc. So these are the different ways by which we can produce zinc oxide film. Now, coming to the growth of the zinc oxide nanostructures, as has been told previously, that zinc oxide is probably the most versatile material in terms of the different shapes of nanostructure it can produce. So, say it can be in the form of an hexagon, like here, it can be in the form of wires, tetrapods, so on and so forth. So, a lot of possibilities are there for zinc oxide to be in different state. Okay. So, coming to the applications of zinc oxide structures, they are used in sensing application where their piezoelectric nature is used, and especially in bio and gas sensing, zinc oxide plays an important role. Now, they can detect, since piezoelectric sensor is used, they can detect a measure of the current flow uh, through the nanostructure. So, a current flow flowing through the nanostructure, they, in response to a very small deflection, gets captured in the nano-based sensors, and this mechanism is used in making. Sorry, not it would be directing the blood pressure in the blood. The advantage being the zinc oxide is biocompatible. Another application of zinc oxide is in field emission transistor, where the zinc oxide plays a role in changing the conductance between the source and the drain, and by bending the nanostructured array, and which actually leads to formation of the gate voltage. And this is one of the recent discoveries, and it could even eliminate batteries supplying power supplies. Other applications of zinc oxide are in DNA sensing, a nanowire for zinc oxide solar cell, when combined with the flexible substrate, giving it more stability and increased photon capture. And in terms of gas sensing, uh, ppm level of acetone and ethanol have been reported to be detected by the zinc oxide based nano nanosensors. The high sensitivity of zinc oxide often plays a role in enhancing its sensing capabilities.